Look up at the night sky, and you'll see countless stars shimmering like distant diamonds, each one a tiny pinprick of light in the vast cosmic canvas. But don't let their quiet glow fool you. Behind that tranquil twinkle lies unimaginable power, forces so immense they defy human comprehension. Stars aren't just pretty lights, they're titanic furnaces, celestial giants that shape the very fabric of the universe. And among them, a rare few stand apart monsters of energy, behemoths so fierce they rewrite the rules of physics just by existing. Imagine standing on a planet orbiting one of these cosmic powerhouses. The sky wouldn't just be bright, it would be ablaze, seared by radiation so intense it could strip atmospheres and boil oceans in seconds. These aren't just stars, they're supercharged engines of creation and destruction, some burning millions of times brighter than our own sun, others so massive they could swallow entire solar systems without a second thought. How do they work? What makes them so extraordinarily powerful? And which ones reign supreme in the universe's hierarchy of stellar might? That's exactly what we're about to uncover. Over the course of this journey, we'll count down the 30 most powerful stars ever discovered, from runaway hypergiants to mysterious, energy-spewing anomalies that leave scientists speechless. You'll learn why some stars shine with the fury of a trillion suns, how they bend space and time around them, and what happens when their colossal lives finally come to an end. This isn't just a list, it's a voyage to the edge of what's possible, a glimpse into the most extreme corners of the cosmos. So buckle up. The universe is about to reveal its brightest, most violent, and utterly magnificent champions. Right at the top of our countdown sits a star so colossal it makes our sun look like a speck of dust. UY Scuti, the reigning king of cosmic giants. If you were to place this monster at the center of our solar system, its surface would stretch beyond the orbit of Jupiter, swallowing Mercury, Venus, Earth, and Mars without breaking a sweat. Just how big is that? Picture a sphere over 1,700 times wider than the sun. A titan so vast light takes hours to travel from one side to the other. But size isn't the only thing that makes UY Scuti jaw-dropping. This star burns with a luminosity over 300,000 times brighter than our sun, pumping out enough energy in a single second to power human civilization for centuries. It's a red supergiant, a phase in a star's life where it expands to staggering proportions while fusing heavier elements in its core. That's the secret behind its power, a celestial engine churning through nuclear fuel at an unsustainable rate, destined to meet a cataclysmic end. You'll find UY Scuti lurking in the constellation Scutum, a faint shield-shaped patch of sky near the Milky Way's core. Though it appears as just a dim red dot from Earth, don't let that fool you. Its apparent faintness comes from sheer distance. It's over 9,000 light-years away. If this star were as close as Alpha Centauri, it would dominate our sky, casting shadows even at night. What truly sets UY Scuti apart is its volatility. Stars this massive live fast and die hard. It's already shedding colossal amounts of material, shrouding itself in a nebula of its own making. And when its time comes, it won't fade quietly, it'll explode as one of the universe's most spectacular supernova, briefly outshining entire galaxies. For now, though, it stands as a breathtaking reminder of the raw, untamed power lurking in the cosmos. The Canis Majoris makes even the mightiest stars look modest, a hypergiant so unstable it's literally tearing itself apart. Located in the constellation Canis Major, this cosmic leviathan is one of the most luminous stars known, shining over 270,000 times brighter than our sun. But what truly sets it apart isn't just its brilliance, it's the sheer violence of its existence. Unlike steady burning stars, the Canis Majoris is a pulsating inferno, swelling and shrinking in erratic cycles that unleash devastating energy bursts. Every few decades, this star convulses, ejecting massive clouds of gas and dust in eruptions so powerful they could swallow entire planets. Astronomers estimate it shedding 30 times Earth's mass worth of material each year, a rate so extreme the star has already sloughed off enough matter to form a small nebula around itself. Picture a colossal heartbeat, each pulse hurling enough material into space to build a dozen solar systems. These explosions aren't just spectacular, they're reshaping the star's future, stripping it layer by layer until only a doomed core remains. Finding UY Canis Majoris requires looking southward near the constellation's nose. Despite its staggering size, over 1,400 times wider than the Sun, it appears deceptively faint from Earth, its light dimmed by distance and the very dust it's spewing. If placed in our solar system, its surface would extend beyond Saturn's orbit, leaving no room for the inner planets. The star's fate is sealed. Within the next 100,000 years, a blink in cosmic terms, its core will collapse, triggering a supernova so colossal it could outshine the Milky Way for weeks. The aftermath, either a neutron star spinning at unimaginable speeds or a black hole hungry enough to devour nearby worlds. For now, though, UY Canis Majoris rages on, a breathtaking reminder of how fleeting even the mightiest stars can be. Betelgeuse isn't just another star in the sky, it's a ticking time bomb. A red supergiant so unpredictable it keeps astronomers on edge. Glowing ominously in Orion's shoulder, this colossal star has fascinated civilizations for millennia, from ancient Egyptians linking it to Osiris to Polynesian navigators using it as a celestial guide. But what really captures modern attention is its bizarre behavior. In late 2019, Betelgeuse dimmed dramatically, losing nearly 2/3 of its usual brightness in just months. The event sparked a frenzy. Was this the prelude to a supernova, a cosmic spectacle unseen in our galaxy since Kepler's star in 1604? The truth turned out to be stranger. Betelgeuse didn't explode instead, it coughed. Observations revealed the dimming was caused by a colossal plume of dust, ejected as the star's surface convulsed. Picture a volcano belching ash, but on a stellar scale. A cloud so vast it temporarily blocked Betelgeuse's light from reaching Earth. This isn't unusual for aging supergiants. Betelgeuse is a pulsating variable star, swelling and shrinking like a cosmic lung as it burns through its final reserves of fuel. Each pulse hurls material into space, creating a swirling nebula of debris around it. What makes Betelgeuse truly extraordinary is its sheer scale. If placed at our solar system's center, it would engulf Mercury, Venus, Earth, and Mars, stretching beyond the asteroid belt. Its luminosity fluctuates between 90,000 and 150,000 times brighter than the Sun, a variability visible even to the naked eye. That's why Orion's shoulder appears to twinkle with a distinct orange hue, a telltale sign of a star in its death throes, and death is coming. Betelgeuse is racing toward a supernova, likely within the next 100,000 years. When it happens, the explosion will be so bright it could outshine the moon, casting shadows on Earth even during the day. For weeks, it might be visible in broad daylight, a second sun blazing in the sky. The aftermath, either a neutron star spinning furiously or a black hole lurking in Orion's silhouette. Until then, Betelgeuse remains a dazzling enigma, a reminder that even the most familiar stars harbor explosive secrets. While Betelgeuse burns with ominous orange intensity, its celestial neighbor Rigel offers a stunning contrast, a searing blue supergiant blazing at the opposite end of the stellar spectrum. Where Betelgeuse pulses with the unstable energy of a star nearing its end, Rigel shines with the fierce brilliance of youth, radiating enough ultraviolet light to ionize entire swaths of space. This is no aging giant, it's a powerhouse in its prime, dominating Orion's left foot with a luminosity 40,000 times greater than our Sun. What makes Rigel truly remarkable is its role as a cosmic lighthouse. Its intense radiation bathes the nearby Orion Nebula, energizing the gas and dust to glow like a celestial watercolor. Without Rigel's blistering light, this stellar nursery where new stars are born would remain shrouded in darkness. The star's sheer power sculpts the nebula itself, carving cavities in the cosmic clouds as its stellar winds blast outward at staggering speeds. From Earth, Rigel is unmistakable, the seventh brightest star in our night sky, visible even in light-polluted cities. Stargazers have marveled at its blue-white radiance for millennia, though its distance of over 860 light-years means the light we see today left the star around the time the Magna Carta was signed. Despite that vast gap, its brightness makes it a cornerstone of Orion's iconic shape, forming a striking counterbalance to Betelgeuse's ruddy glow. But Rigel's splendor hides a violent truth. Stars this massive burn through their fuel at a breakneck pace. In just a few million years, a brief moment in cosmic terms, it will exhaust its nuclear resources, likely ending its life in a cataclysmic supernova. Until then, Rigel remains a beacon of raw stellar power, a dazzling reminder that even in the same constellation, stars can be as different as fire and ice. Eta Carinae isn't just a star, it's a cosmic catastrophe waiting to happen. This volatile binary system, located 7,500 light-years away in the constellation Carinae, makes even the most unstable stars seem tame by comparison. What sets it apart is the sheer scale of its tantrums. In the 1840s, Eta Carinae erupted with such violence that it briefly became the second brightest object in the night sky, outshone only by Sirius despite being hundreds of times farther away. Astronomers call this event the Great Eruption, a decades-long outburst where the star spat out enough material to form 10 suns, creating the spectacular homunculus nebula we see today. Hubble's images of this nebula reveal a breathtaking hourglass shape, twin lobes of gas and dust expanding outward at over 1.5 million miles per hour. The structure resembles a cosmic butterfly frozen mid-flight, its wings stretching a light-year across. This isn't just stellar debris, it's a time capsule, preserving the moment when Eta Carinae nearly tore itself apart. The nebula glows not from starlight but from within, as shockwaves heat the ejected material to millions of degrees. But the real terror lies in what's coming. Eta Carinae's primary star weighs in at over 100 solar masses, hovering dangerously close to the theoretical limit where stars become unstable. Current models suggest it could detonate as a hypernova, an explosion so energetic it would dwarf typical supernova. When this happens, the blast could unleash gamma-ray bursts intense enough to strip away Earth's ozone layer if aimed our way, though fortunately we're safely out of the firing line. For now, the system continues its bizarre dance. Every 5.5 years, the two stars swing perilously close, their colliding stellar winds generating X-ray flares that spike brighter than most stars in our galaxy. Each pass could be the trigger for disaster, making Eta Carinae one of the most unpredictable and fascinating time bombs in our cosmic neighborhood. WR-102 is the universe's way of showing off its most extreme chemistry lab, a Wolf-Rayet star that's essentially a cosmic forge, blasting out elements at speeds that defy imagination. Nestled in the constellation Sagittarius, this star doesn't just burn. It rages, hurling its own atmosphere into space at nearly 6 million miles per hour. To put that into perspective, if Earth were orbiting WR-102, these stellar winds would strip our planet down to its core in minutes. But what makes this star truly special isn't just its violence, it's what those winds carry. Unlike most stars that spew mainly hydrogen and helium, WR-102 outer layers are laced with staggering amounts of oxygen, carbon, and nitrogen, elements normally buried deep in a star's core. Scientists call this rare breed of star a WO-type Wolf-Rayet, one of only 8 known in our galaxy. The oxygen-rich spectrum is like a cosmic fingerprint, revealing a star in its final, desperate throes. As WR-102 fuses heavier elements in its core, titanic pressures force them to the surface, where the star's ferocious winds catapult them into interstellar space. This isn't just a stellar death rattle, it's a delivery system for the building blocks of planets, life, and even future stars. Every atom of oxygen you're breathing right now likely passed through the heart of a star like this billions of years ago. The clock is ticking for WR102. Wolf-Rayet stars are stellar sprinters, brilliant, fast-lived, and doomed. Within the next few 100,000 years, this star will likely collapse in a supernova so powerful it could outshine entire galaxies. The explosion will scatter its enriched guts even farther, seeding nearby nebulae with the very elements needed to form rocky planets and potentially life. For now, WR102 continues its wild dance on the edge of destruction, a dazzling reminder that even in death, stars shape the universe's future. Hidden in the dense star fields near our galaxy's core, the Pistol star earns its name from the eerie, pistol-shaped nebula that surrounds it, a cosmic fingerprint left by its violent outbursts. Discovered by the Hubble Space Telescope in the 1990s, this star defies belief with a luminosity 10 million times greater than our Sun. To grasp that number, think of every star visible to the naked eye on a clear night combined. Their total light wouldn't come close to matching this single celestial titan. Hubble's keen eye revealed the Pistol star's true nature despite its cloak of interstellar dust. Nestled within the quintuplet cluster, a star-studded gathering near Sagittarius A, our galaxy's supermassive black hole, this blue hypergiant is thought to have formed in a frenzy of stellar births. The quintuplet cluster is a cosmic pressure cooker where crowding and intense radiation create the perfect conditions for monster stars. Here, gravitational tug-of-wars and catastrophic collisions may have birthed the Pistol star, sculpting it into one of the most energetic objects in the Milky Way. What makes this star especially fascinating is its volatility. Around 4,000 years ago, it ejected shells of gas equivalent to 10 suns in an event so violent it carved the pistol-shaped nebula we see today. The star's winds blast outward at nearly 100 billion miles per hour, carrying enough force to reshape entire sectors of space. Even now, it's shedding mass at a rate that would vaporize Earth's oceans in seconds if we were nearby. Yet for all its power, the Pistol star is living on borrowed time. Hypergiants this massive burn through their fuel in just a few million years, destined to end as supernova, or perhaps even hypernova, capable of emitting lethal gamma-ray bursts. Until then, it stands as a dazzling testament to the extremes of stellar life, a beacon of raw energy lurking in the galaxy's crowded heart. Rho Cassiopeiae isn't your average star, it's a temperamental yellow hypergiant with a habit of throwing cosmic tantrums. While most stars quietly burn for billions of years, this unpredictable behemoth nestled in the constellation Cassiopeia erupts with the violence of a celestial volcano. In 1946, astronomers witnessed one of its most dramatic outbursts when it suddenly brightened before ejecting a chunk of its outer layers into space. Imagine a star coughing up enough material to form 3 Earth-sized planets in one go. That's the scale of Rho Cassiopeiae's fury. These eruptions aren't random acts of stellar rage. They're critical clues to understanding how the most massive stars evolve. Yellow hypergiants like Rho Cassiopeiae occupy a brief, unstable phase between burning hydrogen and helium, a cosmic tightrope walk where even slight imbalances trigger violent convulsions. The 1946 event wasn't just a light show. It revealed how these stars shed mass in fits and starts, leaving behind telltale chemical signatures in their ejected material. When astronomers analyzed the outburst's aftermath, they found traces of titanium oxide, a smoking gun that proved the star was literally tearing itself apart from within. What makes Rho Cassiopeiae especially fascinating is its rarity. Fewer than 20 yellow hypergiants are known in our galaxy, making each eruption a precious chance to study stellar life cycles under extreme conditions. The star's surface churns like a boiling cauldron, with convection currents so powerful they could swallow entire solar systems. Its temperature swings wildly too, varying by thousands of degrees over mere decades, another sign of its precarious balance between expansion and collapse. Living over 3,000 light-years away, Rho Cassiopeiae poses no threat to Earth, but its eruptions serve as a stark reminder. Even the brightest stars can't escape their fate. Every outburst brings it closer to a final, cataclysmic supernova, one that will enrich the galaxy with heavy elements while leaving behind either a neutron star or a black hole. For now, though, it continues its erratic dance, offering astronomers a front-row seat to one of the universe's most spectacular shows. Mu Cephei glows like a burning ember stranded in the cosmos, a star so vividly red that 18th-century astronomer William Herschel described it as a very fine, deep garnet color. This isn't just another twinkling dot in the constellation Cepheus. It's one of the largest and most luminous cool supergiants known, a crimson titan radiating with the energy of over 38,000 suns. What gives Mu Cephei its striking hue isn't just surface temperature, though at around 3,700 Kelvin, it's far cooler than our yellow sun, but its sheer size. The star's outer layers have expanded to over 1,000 times the sun's diameter, creating an atmosphere so thin and diffuse that light passes through it like sunset rays filtering through smoke. Beneath that mesmerizing garnet glow lies a nuclear cauldron in overdrive. Mu Cephei belongs to a rare class of pulsating variable stars, its brightness shifting unpredictably as fusion reactions in its core grow increasingly unstable. Unlike younger stars that steadily burn hydrogen, this aging giant has progressed to fusing heavier elements, helium, carbon, even oxygen, in layered shells around its core. Each fusion stage releases bursts of energy that make the star's entire structure shudder, causing its outer layers to expand and contract in rhythms that can last years. Astronomers compare these convulsions to a pot of water nearing boiling point, bubbles of energy rising and disrupting the surface before bursting violently into space. The star's variability isn't just a light show, it's a death knell. Mu Cephei has maybe a few 100,000 years left before its core collapses, triggering a supernova that will briefly outshine the Milky Way. Until then, it offers astronomers a front-row seat to stellar evolution's final act. Even amateur stargazers can spot its rich color with binoculars, a ruby pinpoint contrasting against the glittering blues and whites of neighboring stars. In that garnet glow, we're witnessing a cosmic metamorphosis, the same process that forged the calcium in our bones and the iron in our blood, playing out on a scale almost too grand to fathom. VV Cephei is a celestial odd couple, a red supergiant so enormous it makes its blue companion star look like a speck in comparison. This bizarre binary system, located about 5,000 light-years away in the constellation Cepheus, showcases one of the most extreme size differences ever observed between two stars. If you were to place VV Cephei at the center of our solar system, its outer atmosphere would stretch beyond Jupiter's orbit, while its smaller companion would barely clear Mercury's path. The red supergiant alone is estimated to be over 1,000 times wider than our Sun, a bloated, aging star leaking gas into space as it nears the end of its life. What makes this pair truly remarkable is their gravitational tango. Every 20 years or so, the smaller blue star dives deep into the supergiant's outer layers, skimming so close it actually plows through the diffuse, ruby-hued atmosphere. As it orbits, the companion star siphons off vast quantities of material, creating swirling streams of hot gas that spiral between them. These aren't gentle exchanges. Think of a hurricane tearing chunks from a cloud, only on a cosmic scale. The stolen matter forms an accretion disk around the smaller star, superheating until it emits intense X-rays detectable across interstellar space. But VV Cephei isn't just losing mass, it's losing time. Each pass by its companion speeds up the supergiant's inevitable collapse. the system has already ejected enough material to form multiple stars, leaving behind a glowing trail of ionized gas. Eventually, when the red supergiant exhausts its fuel, the resulting supernova won't just destroy one star. It could destabilize the entire binary system, flinging its companion into the void or triggering a second explosion. For now, though, their lopsided dance continues, a fleeting spectacle of cosmic theft played out against the backdrop of deep space. KW Sagittarii looms in the galactic core like a ruby set against black velvet, a red supergiant so immense it pushes the limits of what astronomers thought possible for stellar size. Nestled 9,800 light-years away in the constellation Sagittarius, this colossal star measures roughly 1,460 times wider than our Sun. To grasp that scale, picture this: if KW Sagittarii replaced our Sun, its surface would extend beyond the orbit of Jupiter, swallowing Mercury, Venus, Earth, and Mars without hesitation. Its sheer girth isn't just impressive, it's scientifically baffling. Current stellar models struggle to explain how stars can balloon to such extremes without tearing themselves apart. The star's staggering dimensions aren't its only mystery. KW Sagittarii pulses with an irregular rhythm, its brightness flickering as its unstable outer layers expand and contract like a cosmic heartbeat. This isn't gentle swelling, it's the sign of a star in crisis, burning through its nuclear fuel at an unsustainable pace. Deep in its core, fusion reactions have progressed far beyond hydrogen, now forging heavier elements like carbon and oxygen in a desperate bid to stave off collapse. Each convulsion hurls massive amounts of material into space, shrouding the star in a hazy cocoon of dust and gas that dims its light from our perspective. What truly captivates astronomers is how KW Sagittarii defies expectations. Stars this massive shouldn't last long enough to reach such outrageous sizes. Theoretical predictions suggest they'd shed their outer layers or explode long before inflating to these proportions. Yet here it stands, a cosmic anomaly challenging our understanding of stellar life cycles. Its existence hints at gaps in our knowledge, perhaps undiscovered physics governing how the most massive stars evolve when left to their own devices in the galaxy's crowded central regions. Despite its brilliance shining with the luminosity of over 200,000 suns, KW Sagittarii appears deceptively faint from Earth. Interstellar dust between us and the galactic center absorbs much of its light, leaving only a dim reddish pinpoint visible through telescopes. That obscurity makes every detail we can glean precious, offering clues about the violent, short lives of stars born in the Milky Way's most densely packed stellar nurseries. One thing's certain: when this giant finally meets its end, the resulting supernova will be a spectacle for the ages. A flash of light that, for a brief moment, could outshine entire galaxies. KY Cygni stands as one of the most hotly debated stars in modern astronomy, not because of its behavior, but because of its baffling, ever-changing size estimates. This crimson supergiant, nestled in the constellation Cygnus, has been measured anywhere from 1,000 to 1,500 times the Sun's radius, a discrepancy so vast it could swallow entire planetary orbits. The confusion isn't due to sloppy science. It reveals just how tricky measuring distant stars can be when they're cloaked in their own boiling atmospheres and drifting dust. To understand the controversy, picture KY Cygni as a flickering bonfire in a smoky room. Astronomers can't just point a ruler at it. They rely on indirect methods, primarily analyzing the star's light and temperature. One common approach involves measuring its angular diameter, how large it appears from Earth, and combining that with its distance. But KY Cygni's outer layers are so diffuse and turbulent that its edge is more like a fading whisper than a sharp boundary. Depending on which wavelength of light they observe, researchers get wildly different estimates, like trying to gauge the size of a cloud by staring at it through different colored filters. Adding to the challenge is the star's location in the crowded Cygnus constellation, where interstellar dust dims and reddens its light. Some measurements account for this dust, others don't, leading to further disagreement. Then there's UY Scuti's pulsations. It swells and shrinks unpredictably, meaning its size today might not match last decade's observations. The star's luminosity, blazing up to 140,000 times brighter than the Sun, only complicates things further as intense radiation pressure distorts its apparent shape. Despite the debate, one fact remains undisputed. UY Scuti is a monster nearing its explosive end. Whether it's a mere 1,000 solar radii or half again as large, this supergiant's sheer scale defies earthly intuition. Every conflicting measurement teaches astronomers something new about stellar atmospheres, cosmic dust, and the limits of our observational tools. UY Scuti isn't just a star, it's a masterclass in cosmic humility, reminding us that even in an age of advanced telescopes, the universe keeps its grandest secrets closely guarded. Antares burns in the night sky like a fiery rival to Mars, its deep red glow so striking that ancient astronomers named it Anti-Ares, literally the rival of Mars. This crimson supergiant anchors the heart of the Scorpius constellation, pulsing with an intensity that makes the nearby red planet seem pale by comparison. The resemblance isn't just visual. Both objects get their ruddy hues from iron-rich surfaces, but where Mars wears its rust like a coating of dust, Antares' color comes from something far more dramatic, the star's own swelling, cooling outer layers. Unlike the steady glow of younger stars, Antares is a cosmic time bomb, its core fusing heavier elements in a desperate bid to stave off collapse. This isn't a peaceful process. The star's outer atmosphere churns like a boiling ocean, ejecting massive plumes of gas that travel at speeds up to 12 miles per second. These aren't gentle breezes, they're hurricane-force winds strong enough to strip planets of their atmospheres, carving intricate structures into the surrounding Rho-Ophiuchi cloud complex. Hubble images reveal these sculpted tendrils of dust and gas glowing in Antares' reflected light, a celestial gallery shaped by stellar fury. The clock is ticking for this scarlet giant. In perhaps as little as 1,000,000 years, a blink in cosmic terms, its core will exhaust its nuclear fuel, triggering one of the most spectacular supernova our galaxy has ever witnessed. When that happens, the explosion will briefly outshine the full moon, visible even in daylight. But Antares isn't just waiting to die, it's actively seeding its future. The very material it's blowing off today will become the building blocks for new stars, planets, and potentially even life. What makes Antares especially fascinating is its duality. Through telescopes, it reveals itself not as a single point of light, but as a binary system. Its smaller, blue-green companion star hides in the primary's glare, orbiting just 500 astronomical units away, close enough that astronomers suspect it may have influenced Antares' violent mass loss. Together, they form a cosmic odd couple, one fading as the other burns brilliant and hot. For now, Antares remains a beacon in our summer skies, a reminder that even the grandest stars are fleeting and that their deaths pave the way for new beginnings. Deneb shines as the crowning jewel of the summer triangle, a blue-white supergiant so luminous it's visible across 2,600 light-years of space. Unlike most stars where distance dims their brilliance, Deneb defies expectation, its light piercing through interstellar dust with the intensity of 54,000 suns combined. Positioned at the tail of Cygnus the Swan, this stellar beacon serves a purpose far beyond celestial decoration. Astronomers rely on Deneb as a standard candle, a cosmic yardstick for measuring the vast emptiness between galaxies. The secret lies in its predictable behavior. Deneb belongs to the rare class of Alpha Cygni variable stars that pulse rhythmically, their brightness fluctuating in ways scientists can decode like Morse code from the universe. By studying these subtle pulsations and comparing them to nearby stars with known distances, astronomers calibrate Deneb's true luminosity. Once they establish that baseline, they can spot similar stars in distant galaxies, using them as signposts to map the expanding universe itself. It's cosmic triangulation at its most elegant, with Deneb as the fundamental reference point. But what makes Deneb extraordinary isn't just its usefulness, it's the sheer improbability of its existence. The star burns through its nuclear fuel at a staggering rate, losing mass equivalent to one Earth every 300 years through its mighty stellar winds. Given its size over 200 times wider than our Sun, you'd expect such a bloated giant to be unstable. Yet Deneb maintains remarkable equilibrium, its outward radiation pressure perfectly balancing the inward pull of gravity for now. This delicate dance can't last forever. In mere millions of years, Deneb will likely explode as a brilliant supernova, temporarily outshining entire galaxies before collapsing into a dense neutron star. For skywatchers, Deneb offers more than scientific intrigue. On clear summer nights, it anchors one vertex of the summer triangle alongside Vega and Altair, forming a celestial pyramid visible from both hemispheres. Its blue-white glow cuts through light pollution better than most stars, a testament to its incredible power. Through binoculars, keen observers might notice its subtle twinkle, not an atmospheric effect, but the literal flickering of a dying giant breathing its last before cosmic time runs out. In Deneb, we witness both a tool for understanding the universe's structure and a fleeting masterpiece of stellar evolution. Sigma Octantis may not dazzle like Betelgeuse or Rigel, but this unassuming star holds a position of cosmic importance. It's the southern counterpart to Polaris, marking the celestial South Pole. While it shines a mere 25 times brighter than our Sun, its steady glow has guided explorers across the southern hemisphere for centuries, a silent sentinel in the constellation Octans. Unlike its northern cousin Polaris, which gleams prominently as the 51st brightest star in the night sky, Sigma Octantis is so faint it's nearly invisible to the naked eye under light-polluted skies. Yet this contrast in brilliance reveals a fascinating truth. Power in the universe isn't always about raw luminosity. Sometimes it's about precision and position. What makes Sigma Octantis extraordinary is its unwavering place in the sky. As Earth spins, southern constellations wheel around it like hands on a clock, while this humble star remains fixed within 1 degree of the celestial pole. Navigators relying on it don't need its light to be intense, they need it to be reliable. Polynesian voyagers, Antarctic explorers, and even modern astronomers calibrating telescopes all depend on its constancy. The star's faintness actually works in its favor. Unlike flashier stars that twinkle or vary, Sigma Octantis burns with a consistency that's almost mechanical. The difference between Sigma Octantis and Polaris tells a deeper story about stellar diversity. Polaris is a yellow supergiant, a massive, evolving star with a luminosity 2,500 times greater than our Sun. Sigma Octantis, by contrast, is a white main sequence star, smaller and far more stable. Their roles as pole stars aren't permanent either. Earth's axial wobble means Polaris will drift away from true north in a few thousand years, while Sigma Octantis' alignment is already slipping by tiny fractions each year. For now, though, these two stars, one blazing, one subtle, serve as celestial bookends, proving that in the cosmos, significance comes in many forms. Whether guiding ships across stormy seas or helping telescopes peer into the void, sometimes the quietest stars have the loudest impact. S Doradus doesn't just shine, it rebels. Nestled in the large Magellanic Cloud, a satellite galaxy dancing around our Milky Way, this luminous blue variable star defies one of astrophysics' fundamental rules, the Eddington luminosity limit. That limit represents the maximum brightness a star can theoretically achieve before radiation pressure overwhelms gravity, tearing the star apart. Yet S Doradus doesn't just flirt with this boundary, it smashes through it during violent outbursts that leave astronomers questioning their models. These eruptions transform S Doradus from a brilliant star into something resembling a supernova in slow motion. Over months or years, its brightness surges as it ejects shells of material, expanding its outer layers until the star's diameter balloons to staggering proportions. At its peak, it can outshine every other star in its host galaxy combined. Then, just as unpredictably, it contracts again, fading back to relative obscurity. This isn't the steady flicker of a variable star. It's the celestial equivalent of a pressure cooker intermittently blowing its lid. What makes S Doradus outbursts even more perplexing is their mechanism. Normally, stars obey the Eddington limit because their gravity keeps radiation in check. But S Doradus seems to cheat, somehow stabilizing itself even as its luminosity soars past the theoretical maximum. One leading theory suggests its eruptions create temporary porosity in its outer layers, like a sponge that lets excess radiation escape without destroying the star's structure. Another proposes that its intense magnetic fields channel the energy, funneling it away like lightning rods diverting a storm. Then there's the star's environment to consider. Floating in the metal-poor Large Magellanic Cloud, S Doradus formed from primordial gas with fewer heavy elements than stars in our galaxy. This unique composition might allow it to puff up more easily, its outer layers less dense and more prone to expansion. Every eruption enriches its surroundings with fresh elements, contributing to the chemical diversity of its dwarf galaxy. Ultimately, S Doradus serves as both a mystery and a laboratory. Its existence challenges our understanding of stellar physics while offering clues about how the first generation of stars, monsters even more massive and unstable, shaped the early universe. Each outburst writes a new chapter in the story of how stars push against the limits of their own destruction, proving that in the cosmos, even the most established rules have exceptions. R136A1 shatters every notion of what a star should be, a cosmic heavyweight tipping the scales at 265 times the mass of our Sun, so colossal it forced astronomers to rewrite the rulebook on stellar formation. Lurking in the Tarantula Nebula, 163,000 light-years away in the Large Magellanic Cloud, this blue hypergiant isn't just big, it's borderline impossible. Before its discovery, scientists believed stars couldn't exceed 150 solar masses. R136A1 bulldozed that limit, proving the universe operates on a scale far grander than our models predicted. What makes this star truly bewildering isn't just its current heft, it's how much weight it's already shed. Researchers estimate R136A1 was born with over 320 solar masses, meaning it spent its short, violent life slimming down at a staggering rate. Its stellar winds blast outward at nearly 6 million miles per hour, ejecting Earth's worth of mass every 22 days. Picture a hurricane tearing through a sandcastle, but instead of sand, it's the star's own flesh being hurled into the void. These winds glow with the intensity of a small galaxy, ionizing surrounding gas into psychedelic swirls visible across interstellar distances. The star's brilliance is equally mind-numbing. Shining with the luminosity of nearly 9 million suns, R136A1 emits more energy in 5 seconds than our star will across its entire 10 billion-year lifespan. If placed in our solar system, even at Pluto's distance, its ultraviolet radiation would vaporize Earth's atmosphere instantly. This isn't just a star, it's a cosmic blowtorch, relentlessly sculpting its nebula and sterilizing any potential planets within hundreds of light years. Yet R136A1's most profound impact isn't on its surroundings, it's on science itself. Its existence suggests that star-forming regions with dense, metal-poor gas, like the Tarantula Nebula, can birth behemoths we once thought were theoretical. These monsters likely dominated the early universe, their short lives seeding space with heavy elements that became the building blocks for planets and life. But don't expect R136A1 to stick around for study. Stars this massive live fast and die young. In another million years, a cosmic eye blink it'll likely detonate as a pair instability supernova, an explosion so violent it leaves no remnant behind, just a void where a titan once roared. For now, it stands as a defiant challenge to our understanding, a reminder that the universe always has more extreme laboratories than our textbooks dare to imagine. HD 93129A doesn't just light up the Carinae Nebula, it electrifies it. This blue hypergiant, part of a rare triple-star system, bombards its surroundings with ultraviolet radiation so intense it acts like a cosmic sculptor, ionizing vast clouds of gas into glowing pillars and caverns. Located 7,500 light-years away, HD 93129A is the primary engine behind one of the most visually stunning regions in our galaxy, the Carinae Nebula. But what makes it truly extraordinary isn't just its brilliance, it's the way its energy transforms the very fabric of its stellar neighborhood. The star's ultraviolet output is off the charts, several million times stronger than our sun's. This isn't just light, it's a relentless barrage of high-energy photons that strip electrons from hydrogen atoms, creating a shimmering plasma halo around the nebula. The process, called photoionization, turns cold, dark gas clouds into radiant tapestries of reds and purples, visible even to amateur telescopes, Hubble's famous pillars of creation like structures in Carinae. Those are HD 93129A's handiwork, its radiation carving away at the nebula like a cosmic chisel while triggering new star formation in the densest pockets of gas. But HD 93129A doesn't work alone. It shares its orbit with two other massive stars in a gravitational dance that amplifies their collective impact. The trio's combined stellar winds particles streaming outward at nearly 2,000 miles per second collide in shock waves that heat surrounding gas to millions of degrees, generating X-rays detectable across interstellar space. These interactions create turbulent bubbles and filaments, giving the Carinae Nebula its intricate, almost frothy appearance. What fascinates astronomers most is the star's precarious balance. Hypergiants like HD 93129A teeter on the edge of stability, their immense radiation pressure nearly strong enough to blow them apart. Yet somehow it persists, offering a rare glimpse into how the universe's most massive stars shape their environments. Every photon it emits carries a message, a blueprint of how light can birth new stars even as it erodes the old. And when HD 93129A finally explodes as a supernova, the shockwave will ripple through the nebula, compressing gas clouds and sparking another generation of stellar giants. For now, it remains a luminous architect, proving that destruction and creation are two sides of the same cosmic coin. P Cygni isn't just another bright spot in the constellation. Cygnus, it's a cosmic fingerprint, a star whose light carries a telltale signature of chaos. This luminous blue variable burns with the intensity of 600,000 suns, but what truly sets it apart isn't its brilliance, it's the bizarre way that light reaches us. When astronomers first analyzed P Cygni's spectrum in the 17th century, they noticed something odd. Its spectral lines weren't clean, crisp marks like most stars. Instead, each line appeared split, with a sharp absorption component shifted toward the blue end of the spectrum, and a broader emission component lingering at the expected wavelength. This peculiar pattern, now called a P Cygni profile, isn't just a quirk, it's a smoking gun, revealing a star violently shedding its own atmosphere into space at breakneck speeds. Break down that spectral fingerprint and you'll uncover a stellar drama. The absorption component forms as light from the star's blazing core passes through expanding shells of gas moving toward us at nearly 100 miles per second. These fast-moving atoms intercept specific wavelengths, leaving dark gaps in the spectrum shifted slightly blueward, the same way a siren's pitch rises as an ambulance races toward you. Meanwhile, the emission component originates from that same gas, but now glowing brightly as it's energized by the star's radiation, the crucial detail. This emission isn't moving toward or away from us, it's radiating in all directions, so it stays at its natural wavelength, creating a luminous counterpart to the absorption dip. Together, these twin features paint a dynamic portrait, a star blowing itself apart in real time, its outer layers unspooling like a cosmic ribbon caught in hurricane-force winds. What makes P Cygni profiles invaluable is their honesty. Unlike static snapshots, they record motion, allowing astronomers to calculate not just what a star is made of, but how its material is moving. Every element leaves its own distinct fingerprint: hydrogen, helium, even rare metals like strontium flinging themselves into the void. By measuring how far the absorption line shifts from its expected position, scientists can clock the expansion velocity of the star's atmosphere down to the meter per second. It's like reading a weather report from halfway across the galaxy, except instead of wind speeds, you're tracking cataclysmic plasma storms capable of vaporizing planets. P Cygni itself serves as the prototype for this phenomenon, but it's far from alone. Similar profiles appear in young, massive stars still swaddled in their natal gas clouds, in aging supergiants on the brink of explosion, even in distant quasars where supermassive black holes shred entire stars into luminous streams. Each one tells the same fundamental story: an object so energetic it can't hold itself together, its outer layers fleeing the very radiation that gives them life. For P Cygni, this turbulence isn't just a phase, it's identity. The star's entire history has been marked by violent outbursts, including a 17th-century eruption that briefly made it the third brightest star in the sky before fading into obscurity for decades. Today, it continues to simmer unpredictably, its spectrum flickering like a candle in a drafty room, a reminder that in the cosmos, even the mightiest stars are at the mercy of their own fury. LBV 1,806 hides in plain sight, a star so brilliant it should dominate our night sky, yet it's practically invisible to the naked eye. Nestled near the galactic center, roughly 30,000 light-years away, this luminous blue variable star blazes with the fury of 5 to 40 million suns. That's not a typo. Its lower estimate already outshines Rigel by 100-fold. The reason we don't see it: a celestial veil of interstellar dust so thick it dims the star's light by a factor of nearly 30 billion. Imagine a lighthouse wrapped in layers of black velvet, its beam reduced to a faint glimmer by the very medium meant to magnify it. What makes LBV 1,806 especially fascinating is how astronomers even found it. Conventional optical telescopes barely registered a blip. Instead, researchers had to rely on infrared and radio observations wavelengths that penetrate dust to uncover its staggering luminosity. The star's light, absorbed by intervening cosmic debris, gets re-radiated as heat, creating a telltale infrared signature. It's like detecting a forest fire by feeling its warmth through dense fog. That indirect approach revealed something extraordinary. LBV 1,806 isn't just bright, it's physics-defying. At its upper luminosity estimates, it challenges the Eddington limit, the theoretical maximum brightness a star can achieve before radiation pressure blows it apart. The implications ripple through astrophysics. Stars this extreme were thought to exist only in the early universe, where pristine gas clouds could collapse into monsters without heavy elements to slow their growth. Yet here's LBV 1,806, a contemporary anomaly suggesting our galaxy might still harbor relics of that violent epoch. Its magnetic field, measured at nearly 200 times stronger than Earth's, adds another puzzle piece. Such intense magnetism could help stabilize the star against self-destruction, channeling its furious winds into structured outflows rather than chaotic bursts. But LBV 1,806 isn't just a laboratory for extreme physics, it's a ticking clock. Stars this massive rarely live beyond a few million years, and this one's violent eruptions hint it's nearing its explosive end. When it goes, the supernova could outshine entire galaxies temporarily, or even collapse directly into a black hole without an explosion. For now, shrouded in dust and raging against cosmic limits, it stands as a humbling reminder. The universe still keeps its brightest secrets hidden in the darkest corners. Theta 1 Orionis C doesn't just light up the Orion Nebula, it commands it. This blistering O-type star, the most massive member of the trapezium cluster, functions like the conductor of a celestial orchestra, its ultraviolet radiance energizing the entire nebula into a glowing masterpiece. What we perceive as the nebula's ethereal glow isn't passive starlight, it's the aftermath of Theta 1 Orionis C's relentless photon assault. Every second, it bombards surrounding hydrogen clouds with enough UV radiation to strip electrons from their atoms, creating a plasma tapestry that fluoresces in pinks and purples visible across 1,500 light-years. But the star's influence stretches far beyond illumination. Its stellar winds hurricanes of charged particles racing outward at over 2,000 miles per second act as cosmic sculptors. These winds carve cavernous bubbles within the nebula, compressing nearby gas into dense ridges where new stars ignite. Even more astonishing is their effect on protoplanetary disks, the birthplaces of future solar systems. Hubble observations reveal these disks as dark smudges silhouetted against the nebula's glow, some warped into teardrop shapes as Theta 1 Orionis C's winds erode them like sandblasters. A few disks even sport comet-like tails, their material being stripped away and recycled into the nebula. Zooming in with 3D simulations, the dynamics grow clearer. Imagine a fledgling planetary system, a rotating disk of gas and dust larger than our solar system suddenly caught in the crossfire. Theta 1 Orionis C's radiation heats the disk's surface, boiling off molecules while its particle winds shear away the outer layers. Over millennia, this relentless erosion can shrink a disk's radius by half, truncating the future planetary system's potential size. Some disks withstand the onslaught thanks to dense cores, others disintegrate entirely, their material joining the nebula's swirling currents. Yet this destruction sparks creation. The same forces that shred disks also trigger shockwaves, compressing nearby gas pockets until they collapse into new stars. Theta 1 Orionis C's fury isn't just chaotic, it's generative, a stellar feedback loop where death and birth intertwine. Through its violence, this single star shapes the trajectory of hundreds of stellar siblings, proving that in the cosmos, even destruction can be a creative act. Zeta Puppis isn't just speeding through space, it's fleeing, a cosmic fugitive tearing through the galaxy at over 60 kilometers per second. This blue supergiant, also known as NOWS, burns with a brilliance 60,000 times greater than our Sun. But what truly sets it apart is the colossal shockwave it leaves in its wake. Like a ship plowing through interstellar waters at impossible speed, Zeta Puppis doesn't just move, it distorts the very fabric of its surroundings, carving a bowshock of heated gas visible in ultraviolet light. The star's breakneck velocity wasn't earned through idle drifting. Most runaway stars get their speed from violent gravitational encounters, either ejected by a supernova's asymmetric explosion or slingshotted by a close brush with a black hole or dense star cluster. In Zeta Puppis' case, evidence points to the latter. Its trajectory traces back to the Vela supernova remnant, suggesting it was once part of a binary system torn apart when its companion star exploded. The energy from that detonation likely sent Zeta Puppis careening across the galaxy, a celestial billiard ball struck by the universe's most powerful cue. What makes this runaway fascinating isn't just its speed but its impact. The star's fierce stellar winds, traveling at 2,400 kilometers per second, collide with slower-moving interstellar gas, creating a visible shock front that glows in X-rays. This structure, resembling a cosmic contrail, stretches over 4 light-years behind the star, a testament to its millennia-long journey. The shockwave does more than just look spectacular. It ionizes surrounding hydrogen, triggering subtle waves of star formation in its path like ripples from a pebble tossed into a pond. Zeta Puppis offers astronomers a rare laboratory. By studying how its high-energy radiation and winds interact with different densities of interstellar material, researchers can simulate conditions similar to the early universe when runaway stars were far more common. Every atom this star's shockwave energizes, every particle it accelerates, contributes to the chemical and dynamic evolution of our galaxy. And its fate is just as dramatic as its past, already shedding mass at a rate millions of times faster than the Sun. It will likely end its life as a supernova, seeding future generations of stars with its heavy elements before vanishing into the void it once raced through. Gamma Velorum isn't just a star, it's a cosmic diamond mine in the sky, a Wolf-Rayet wonder pumping out carbon like a celestial factory. This binary beast, located 1,100 light-years away in the constellation Vela, showcases one of the most chemically bizarre stellar atmospheres ever observed. While most stars cloak themselves in hydrogen and helium, Gamma Velorum's surface is a carbon carnival, its outer layers brimming with soot-like particles that give its light a peculiar fingerprint. This carbon-rich signature isn't just a curiosity. It's the smoking gun of a star tearing itself apart from the inside out, exposing its fusion-forged guts to the universe. The drama unfolds in 2 acts. The primary star, a blue supergiant 20 times more massive than our Sun, whirls around its smaller companion in a gravitational waltz. But the real showstopper is the Wolf-Rayet component, a stellar remnant so luminous its ultraviolet radiation ionizes the surrounding nebula into glowing loops visible through telescopes. Wolf-Rayet stars are stellar exhumations, their hydrogen envelopes stripped away to reveal the elemental layers beneath. Gamma Velorum's carbon-rich spectrum tells us we're witnessing a star in its final defiant phase, having burned through lighter elements and now fusing helium into carbon at a breakneck pace. Every second, its hurricane-force winds blast 1 billion tons of carbon into space, enough to forge diamonds if conditions were right. What makes this system especially terrifying is its fate. Wolf-Rayet stars like Gamma Velorum are ticking time bombs, destined to collapse into gamma-ray bursts, the most energetic explosions since the Big Bang. When its core implodes, the resulting burst could focus twin jets of radiation so intense they'd sterilize planets thousands of light-years away. Luckily for Earth, the system's axis isn't pointed our direction. For now, Gamma Velorum serves as a dazzling preview of our Sun's ultimate fate billions of years from now, after it sheds its outer layers and reveals its carbon-oxygen core. This binary system is both a warning and a wonder, proving even in destruction, stars create the building blocks for cosmic rebirth. Epsilon Aurigae plays a cosmic game of peekaboo like no other star in the sky every 27 years. Its light fades for nearly 2 full years, as if something vast and invisible is sliding silently between us and its glow. This isn't just another eclipsing binary. It's one of astronomy's most enduring puzzles, a celestial detective story that's kept scientists guessing for nearly 2 centuries. At first glance, the system appears straightforward, a luminous F-type supergiant paired with a mysterious companion. But that companion defies explanation. It doesn't glow like a star, doesn't emit detectable heat, and yet it's massive enough to block nearly half the primary star's light during each eclipse. The leading theory paints a surreal picture. Instead of a typical stellar partner, Epsilon Aurigae's dark companion might be a colossal disk of dust and debris, tilted edge-on from our viewpoint. Imagine a vinyl record 1,000 times wider than Earth's orbit, so thick it completely obscures the object at its center. As this disk orbits the bright supergiant every 27 years, it eclipses the star in stages, first dimming gradually as its leading edge encroaches, then maintaining a strangely steady minimum brightness for up to 18 months before slowly brightening again. This peculiar light curve suggests the disk isn't solid. It has a hollow center like a donut, allowing some light to slip through even during mid-eclipse. But mysteries pile up when you look closer. Infrared observations reveal the disk is far hotter than expected for mere dust, hinting at hidden energy sources within. Some researchers propose a pair of tight binary stars lurking at the disk's center, their gravity shaping the surrounding material. Others speculate the disk might be a failed solar system, a protoplanetary nebula that never coalesced into planets, now trapped in an endless dance around its massive primary star. The most tantalizing clue came during the 2009 eclipse, when spectrographs caught unexpected flickering near mid-eclipse, possible evidence of jets or outflows punching through the disk's plane. This 27-year cadence makes each eclipse a generational event in astronomy. The 2009 event marked the first time modern observatories could train Hubble, Spitzer, and ground-based interferometers on the system simultaneously. What they found only deepened the intrigue. The primary star appears smaller and more evolved than previously thought, likely a post-red supergiant contracting toward a helium-burning phase. That revelation reshapes the entire narrative. Epsilon Aurigae might be far older than we imagined, its dark companion a relic from an earlier era when the primary star swelled enough to engulf inner planets or companion stars. What's truly astonishing is how this system defies categorization. Eclipsing binaries typically follow predictable patterns, their light curves as regular as clockwork. Yet Epsilon Aurigae's eclipses vary subtly in duration and depth, suggesting its disk isn't static. It warps, precesses, or even reshapes itself over time. Citizen astronomers worldwide now monitor the star year-round, knowing the next big eclipse won't come until around 2036. Until then, every photon captured carries potential clues, each observation a thread in a cosmic tapestry we're still learning to read. For stargazers, spotting Epsilon Aurigae during an eclipse requires no special equipment. It visibly dims from magnitude 2.9 to 3.8, a change obvious to the naked eye under dark skies. That accessibility makes it a bridge between professional astronomers and backyard observers, a shared puzzle spanning centuries, from its first recorded eclipse in 1821 to the modern era of multi-wavelength astronomy. This star reminds us that even familiar skies hold profound secrets, some taking decades, even lifetimes, to unravel. V838 Monocerotis gave astronomers a once-in-a-lifetime light show in 2002, but what made it extraordinary wasn't just the star's sudden eruption, it was the breathtaking echo that followed. Unlike typical stellar explosions that fade quickly, this one unfolded in slow motion as the blast wave lit up vast shells of surrounding dust like a cosmic chain reaction. Hubble's time-lapse images captured the phenomenon in unprecedented detail, revealing concentric rings of illumination expanding outward at the speed of light, not from the star itself moving, but from its flash being reflected by ever more distant dust layers. The effect resembles a pebble dropped in a pond, with ripples of light instead of water, each ring marking another year of the flash's journey through interstellar space. What made this eruption so baffling was its behavior. Instead of shedding material like a normal nova, V838 Monocerotis seemed to swell catastrophically, temporarily becoming 600,000 times brighter than the Sun, while its outer layers ballooned to diameters rivaling Jupiter's orbit. For a few weeks, it outshone the entire Milky Way, not because it was exploding, but because it was stretching, a peculiar event now classified as a luminous red nova. The leading theory suggests a stellar merger, where two stars collided and merged into one, triggering violent thermal pulses without the typical supernova fireworks. But the real magic lay in the aftermath. As the light echo expanded, it backlit intricate dust structures that had been invisible before, delicate filaments and knots shaped by ancient stellar winds and supernova remnants. Hubble's sharp eye revealed these dust clouds weren't uniform. They formed fractal-like tendrils, evidence of turbulent magnetic fields weaving through interstellar space. Each illuminated layer acted like a celestial CT scan, allowing astronomers to map the nebula's 3D structure for the first time. The event also posed a tantalizing question. Why was there so much dust around V838 Monocerotis in the first place? The prevailing explanation points to the star's earlier eruptions, which may have ejected carbon-rich material that later cooled into dust. Over millennia, these ejecta formed a series of nested shells, like Russian dolls, waiting to be lit up by the 2002 outburst. Today, V838 Monocerotis has faded back into obscurity, but its light echo continues expanding, now over 6 light-years across. Future telescopes may detect its faint reflections for centuries, each ripple a time capsule preserving the moment this enigmatic star chose to reveal the hidden architecture of the cosmos. Eta Carinae hides a terrifying secret. It's a cosmic time bomb waiting to detonate. This unassuming binary system, located 150 light-years away in the constellation Pegasus, consists of 2 stars locked in a deadly dance. A main sequence star similar to our Sun, and a white dwarf packing the mass of our Sun into an Earth-sized sphere. Normally, white dwarfs fade quietly into stellar oblivion, but this one's different. It's greedily siphoning material from its companion, inching closer to a catastrophic tipping point that could unleash one of the most powerful explosions in the universe, a Type Ia supernova. What makes Eta Carinae especially valuable to astronomers isn't just its explosive potential, it's its role as a cosmic measuring stick. Type Ia supernova have a unique property. They all peak at roughly the same intrinsic brightness. This consistency makes them standard candles, celestial lighthouses astronomers use to gauge distances across the universe. When Eta Carinae eventually erupts, its light will provide a benchmark, helping refine calculations of how fast the cosmos is expanding. Imagine a light bulb that always shines at 100 watts. No matter where you place it, you can calculate its distance by how dim it appears. That's how these supernovae illuminate the vastness of space. The process leading to detonation is both methodical and violent. As the white dwarf steals hydrogen from its companion, the stolen gas accumulates on its surface, compressing under immense gravity until it triggers runaway nuclear fusion. This isn't a gentle burn, it's a thermonuclear firestorm that rips the white dwarf apart in seconds, releasing as much energy as our Sun will emit over its entire 10-billion-year lifespan. The explosion would briefly outshine entire galaxies, visible even in daylight from Earth. Yet Eta Carinae's eventual destruction carries a silver lining. The iron, silicon, and other heavy elements forged in its explosion will seed future generations of stars and planets. Meanwhile, its light curve, the precise way its brightness rises and falls, will join a catalogue of similar events, helping astronomers probe dark energy's role in accelerating the universe's expansion. For now, though, this binary system continues its slow-motion countdown, a silent reminder that even the most precise cosmic clocks eventually strike midnight. Alpha Camelopardalis isn't just racing through space, it's a fugitive, a blue supergiant hurtling through the cosmos at speeds that defy logic. Clocking in at over 60 kilometers per second, this stellar outlaw didn't start its life as a lone wanderer. Like a bullet fired from a celestial gun, its trajectory points back to a violent past, an explosive ejection from its birthplace in the open star cluster NGC 1502, nearly 3,000 light-years away. The mechanics behind this stellar escape are as dramatic as they are precise. Imagine a crowded stellar nursery where young, massive stars jostle for position, their gravitational pulls tugging at one another in an unstable dance. Alpha Camelopardalis likely began as part of a binary system, orbiting a companion star until a close encounter with another massive object, perhaps a third star, sent the system into chaos. Gravitational slingshots work like cosmic pinball. When one star gets too close to a pair, the interplay of forces can fling one of them outward at incredible speeds while the others recoil in the opposite direction. For Alpha Camelopardalis, that kick was so powerful it broke free of its cluster entirely, destined to roam the galaxy alone. What makes this runaway especially fascinating is the trail it leaves behind. As the star plows through interstellar space at breakneck velocity, its fierce stellar winds blasting outward at thousands of kilometers per second collide with ambient gas, creating a visible shockwave. This bow shock, similar to the ripple ahead of a speedboat, glows in ultraviolet and X-rays, a telltale sign of a star too restless to stay put. The phenomenon isn't just a light show, it's a breadcrumb trail for astronomers, allowing them to trace the star's path back to its origins with forensic precision. NGC 1502, the cluster Alpha Camelopardalis fled, offers clues to the star's explosive exit. Nestled in the constellation Camelopardalis, this group of young, hot stars is a gravitational pressure cooker where close encounters are inevitable. By studying the motions of the cluster's remaining stars, astronomers have reconstructed the likely scenario, a gravitational tug of war where Alpha Camelopardalis lost its footing and was hurled into the void. The energy required for such an ejection is staggering, equivalent to the force of a supernova, but without the explosion. Yet this runaway speed isn't its only superlative. Shining with the luminosity of over 200,000 suns, Alpha Camelopardalis is a beacon of raw stellar power, its blue-white light cutting through interstellar dust like a cosmic lighthouse. Even as it flees its birthplace, it continues to sculpt its surroundings, its radiation ionizing gas clouds and its winds clearing cavities in the interstellar medium. The fate of such runaway stars is as dramatic as their origins. Unshackled from the dense environments of their birth clusters, they often end their lives in isolation, exploding as supernova far from any stellar siblings. When Alpha Camelopardalis finally exhausts its fuel, its death throes will scatter enriched material across vast, empty regions of space, seeding future star formation in places where few stars dare to venture. For now, it remains a dazzling rogue, a testament to the fact that in the cosmos, even the mightiest stars can be set adrift by the whims of gravity. WR-104 spins through space like a cosmic Catherine wheel, its two massive stars locked in a mesmerizing dance that throws off spiral plumes of scorching gas. This Wolf-Rayet binary, located 8,000 light-years away in Sagittarius, isn't just another stellar duo. It's a celestial timepiece with a potentially deadly secret. Every 8 months, the stars complete their orbital waltz, their colliding stellar winds whipping ejected material into a perfect pinwheel pattern visible in infrared telescopes. But beneath that breathtaking swirl lies a chilling possibility. One of these stars is tipped dangerously toward Earth, its rotational axis possibly aligned with our solar system. The concern stems from the Wolf-Rayet component, a massive, rapidly spinning star shedding its outer layers at nearly 2,000 miles per second. When such stars exhaust their fuel, they don't just collapse into supernova. If conditions are right, their collapse can focus twin jets of gamma radiation along their rotational axes. These gamma-ray bursts are the universe's most powerful explosions since the Big Bang, capable of frying Earth's ozone layer from thousands of light-years away. A direct hit could trigger mass extinctions by allowing deadly ultraviolet radiation to reach the surface unchecked. For years, WR-104 orientation kept astronomers awake at night. Early observations suggested its pinwheel appeared nearly face-on from Earth, a terrifying hint that its rotational pole might point right at us. But recent interferometry studies brought cautious relief. By analyzing the pinwheel's three-dimensional structure, researchers found the system likely tilts between 30 and 40 degrees away from our line of sight. While not perfectly edge-on, this angle almost certainly places Earth safely outside the gamma-ray burst's potential kill zone. the system's distance offers additional comfort. Even if WR-104 Wolf-Rayet star detonated perfectly aligned with Earth tomorrow, 8,000 light-years is considered the outer boundary where a gamma-ray burst could cause significant damage. At that range, the radiation would weaken to roughly the intensity of a solar flare, noticeable to satellites but harmless to life. Yet WR-104 remains an invaluable laboratory. Its exquisite pinwheel pattern lets astronomers measure stellar wind speeds with unprecedented precision, revealing how these violent outflows shape galactic ecosystems. Each rotation etches another layer in the spiral, like rings in a tree trunk recording cosmic weather patterns. And when the Wolf-Rayet star finally explodes, whether in 10,000 years or 100,000, its supernova will momentarily outshine the Moon, a final fireworks display from one of the galaxy's most photogenic binaries. For now, it spins on, a hypnotic whirlpool of plasma reminding us that even the most beautiful cosmic dances can hide lethal potential. T Tauri stars are the infants of the cosmos, flickering, temperamental, and brimming with untapped potential. Named after their prototype in the Taurus constellation, these young stellar objects haven't yet settled into the steady glow of adulthood. Unlike the raging hypergiants we've explored, T Tauri stars are relatively faint, their energy output dwarfed by mature stars. But what makes them extraordinary isn't their current power, it's the promise of what they'll become. Each one is a protostar on the cusp of nuclear ignition, a future sun-like star in the making. Take T Tauri itself, for example. Located about 460 light-years away, it's a chaotic ball of gas still collapsing under its own gravity. Its light isn't generated by the fusion of hydrogen in its core, that hallmark of mature stars, but by the sheer heat of contraction as gravitational energy converts into radiation. This pre-fusion phase means T Tauri stars often flicker unpredictably, their brightness swinging wildly as material from their surrounding accretion disks falls onto their surfaces in violent bursts. Imagine a campfire sputtering to life, sparks flying as it struggles to catch. That's T Tauri's adolescence in stellar terms. What truly sets these stars apart is their environment. Unlike the isolated giants we've seen, T Tauri stars are usually nestled in the stellar nurseries where they were born, surrounded by thick cocoons of gas and dust. Many still have protoplanetary disks, swirling rings of debris that might one day coalesce into planets. Hubble images reveal these disks in stunning detail, some showing gaps where fledgling worlds could already be forming. It's a snapshot of our own solar system's beginnings 4.5 billion years ago. The contrast between a T Tauri star and a mature giant couldn't be starker. While hypergiants like UY Scuti are burning through their fuel at a breakneck pace, destined for explosive deaths, T Tauri stars are just starting their epic journeys. They'll spend the next 100 million years slowly stabilizing, their cores heating until hydrogen fusion begins in earnest. Once that switch flips, they'll enter the main sequence, a phase of relative stability that, for sun-like stars, can last billions of years. Yet, even in their youth, these stars wield surprising influence. Their intense magnetic fields, far stronger than our sun's, generate violent flares and powerful stellar winds, shaping the dynamics of their nascent planetary systems. Some T Tauri stars even exhibit bipolar jets, narrow streams of gas shooting outward at hundreds of kilometers per second, carving intricate pathways through their birth clouds. These jets are cosmic fingerprints, revealing the complex interplay between a star's rotation, magnetism, and infalling material. For astronomers, T Tauri stars are living laboratories. By studying their turbulent surfaces and erratic behavior, scientists can refine models of stellar evolution, piecing together how stars transition from collapsing gas clouds to stable, fusion-powered engines. Every flicker, every flare, every outburst tells a story, one that might hold clues to how our own sun behaved in its infancy and what conditions made Earth's formation possible. So while T Tauri might not win any contests for sheer luminosity today, its significance lies in its potential. Given time, this sputtering young star could become the heart of a solar system not unlike ours, its planets orbiting in the calm that follows the storm of stellar birth. In the grand tapestry of the cosmos, T Tauri reminds us that even the mightiest stars begin as unsteady sparks, and that the universe's most transformative power often lies not in explosive brilliance, but in the slow, steady burn of persistence. Proxima Centauri may be the smallest star on our list, but don't let its humble appearance fool you. This dim red dwarf holds a cosmic significance far beyond its feeble glow. Nestled a mere 4.2 light-years away in the constellation Centaurus, it's our solar system's closest stellar neighbor, a whisper of warmth in the vast interstellar dark. While giants like UY Scuti and R136A1 dominate the power rankings with their sheer enormity, Proxima Centauri proves that stellar influence isn't just about raw energy output. Sometimes proximity and possibility matter more than pure wattage. What this star lacks in brilliance, it makes up for in intrigue. Proxima Centauri is a flare star, prone to sudden, violent eruptions that can double its brightness in minutes. These outbursts unleash torrents of ultraviolet and X-ray radiation, enough to strip the atmosphere from any nearby planet. Yet in a twist of cosmic irony, this very star hosts at least one confirmed exoplanet, Proxima Centauri b, a rocky world nestled in its habitable zone. The paradox is striking. A star capable of sterilizing worlds might also cradle one where liquid water and potentially life could persist. It's a reminder that power in the universe isn't just about destruction, it's also about delicate, improbable balance. The discovery of Proxima Centauri b in 2016 sent shockwaves through the astronomy community. Here was an Earth-sized neighbor, tantalizingly close by galactic standards, orbiting a star we could study in unprecedented detail. While the planet's surface conditions remain debated, bombarded by radiation yet possibly harboring subsurface oceans, its existence reshapes our understanding of where life might take root. Red dwarfs like Proxima Centauri outnumber all other star types combined, meaning if life can endure their tempestuous flares, the galaxy might be far more hospitable than we ever imagined. Yet Proxima Centauri's true power lies in its accessibility. Unlike distant hypergiants, this star is close enough to inspire genuine exploration. Breakthrough Starshot, a bold initiative aiming to send lightweight nanoprobes to Alpha Centauri, Proxima's binary neighbors, could one day give us our first close-up glimpse of another star system. Imagine a spacecraft propelled by laser sails, zipping past Proxima Centauri b within our lifetimes, a feat that would have been pure science fiction just decades ago. So while it barely registers on the cosmic Richter scale of luminosity, Proxima Centauri stands as a quiet revolution. It challenges our obsession with size and might, proving that sometimes the most profound discoveries orbit the faintest stars. In the grand tapestry of stellar power, this unassuming red dwarf weaves a different kind of brilliance, one measured not in solar masses or megaton explosions, but in the tantalizing promise of what might lie just next door. From red supergiants so vast they could swallow our solar system whole to runaway stars hurtling through the galaxy at breakneck speeds, these 30 cosmic powerhouses have redefined what we thought possible. Imagine stars that erupt without warning, bathing entire nebulae in light echoes, or hypergiants so unstable they teeter on the edge of self-destruction, their winds blasting out enough material to forge planets. Some, like R136A1, rewrite the laws of physics with their sheer mass, while others, like Proxima Centauri, prove that even the faintest stars can harbor worlds brimming with possibility. Each of these stellar titans tells a different chapter in the universe's grand story. Take Y Canis Majoris, convulsing as it sheds its own atmosphere in violent bursts, or Eta Carinae, a binary system that behaves more like a celestial demolition derby. Then there's WR-104, spinning like a loaded gun with the potential to unleash a gamma-ray burst, a reminder that beauty in the cosmos often walks hand in hand with danger. But here's the real wonder: this list is just the beginning. Beyond these 30, the universe hides even stranger oddities, stars that defy categorization, like magnetas with magnetic fields strong enough to warp atoms, or zombie stars resurrected from supernova ashes. The cosmos thrives on the extraordinary, and every discovery peels back another layer of the impossible. So which of these stellar titans left you speechless? Was it Antares with its garnet glow and looming supernova? Or perhaps Doradus, the star that laughs in the face of theoretical limits? Drop your favorite in the comments. We're betting the debates will be as fiery as the stars themselves. If this journey through the universe's most powerful stars left you craving more cosmic wonders, you're in luck. Hit subscribe and ring the bell, because we're just getting started. From black holes that rewrite reality to nebulae that paint the sky in light, there's a universe of mysteries waiting to be explored, and we'll be diving deep into every one. Until next time, keep looking up. The cosmos isn't just out there, it's alive with stories, and each one is more breathtaking than the last.